Hello everyone, this is Mirzai from Cal Poly Pomona, and in this lesson we are going to learn sensitivity analysis of a linear programming problem. In the series of videos related to the sensitivity analysis, we are in the part 1 where we talk about simplex matrix math. Before we do sensitivity analysis, it is important to know how we can generate the final optimal table of a simplex for a linear programming problem so that we can reproduce the final table with any change that we make in the initial problem. Suppose you have a maximization problem as a generic form shown on the screen. You'll have n decision variables and m number of constraints. Suppose we found an optimal solution and we know what the basic variables are at the optimal table of the simplex. Then xbv is a vector representing the basic variables and xnbv is a vector that represents the non-basic variables. For example, if I have a maximization problem as shown on the screen, the first step is to standardize this problem. Since all the constraints are in form of less than or equal, the only auxiliary decision variables that we need are slack variables to make this problem standardized. Now, given that in the optimal solution, S1, X3, and X1 are the basic variables, I can form the XBV and XNBV vectors. This is important to remember that we are usually given the basic variables in the optimal solution. Basically, we assume that we have solved this problem, we got into the final table, and we know what the basic variables are. But we want to regenerate the final table without going through the hassle of the simplex table. So the benefit of this is later, by introducing any change in the initial table, we can see the impact in the final table. But for now, please bear with me and see how we can regenerate the final table of the simplex, which is the optimal table, by only having the basic variables in the final table. Given that in the optimal table, S1, X3, and X1 are the basic variables, the vector of XB, or the vector of basic variables, is easy to be formed because we know that these are the three decision variables that are basic. But XNBV is the vector that represents all the decision variables of the problem which are not in the vector of the basic variables. Out of the 6 decision variables, which are X1, X2, X3, and S1, S2, S3, since we don't see S2, S3, and X2 in the set of basic decision variable, we put them in the XNBV. The order of XB and XNBV is not important as far as you keep that order consistent for forming all the related vectors and matrices. So the only important thing is to always keep the consistency in terms of the order of decision variables in your vectors. So far we have this maximization problem. This is the standardized form for the constraints of the problem, and we have the vector of XBV, which represents the basic variables, and XNBV, which represents the non-basic variable. The next definition is the vector of CBV. CBV is a vector representing the objective function coefficients for the optimal table basic variables. The first element in CBV is the coefficient of the first element that you put in your XBV in your objective function. If I look at the objective function here, there is no S1, so the related coefficient, the first element will be 0. If I look at the second element of XBV is X3, and the coefficient of X3 is 20. So I put 20 as the second element of the CBV. If I look at the third element of the XBV, which is X1, the coefficient in the objective function is 60. So I have to put 60 for the third element. So for forming CBV, we have to find the coefficient of every single variables that we are given as the basic variable in the objective function and copy those to form the CBV vector. Similarly, the CNBV is the vector representing the objective function coefficients for the optimal table non-basic variables. Again, this time I have to look for the vector of non-basic variables and find the related coefficient in the objective function. So x2 is the first element. The coefficient of x2 is 30, so the first element will be 30. The second coefficient is s2. s2 doesn't exist in the objective function, so its coefficient is 0. So is the coefficient for S3 because we don't have S3 in the objective function, so its coefficient will be 0. The next vector that we need to know is AJ. AJ is the column of coefficients for the variable xj in the initial table. For example, to form A1, we have to look at the coefficients of the first decision variables in the constraints. If you assume that x1 is the first decision variable in my constraints, this is the vector that represents all the coefficients of x1 in the initial table. So I have to write 842 as A1. Similarly, A2 is the column of the coefficients related to the second decision variable. If I assume x2 is my second decision variable, this vector will be 6, 2, and 1.5. If I assume that the x3 is my third decision variable, the coefficient of x3 in all the constraints form the A3 vector. If I assume that S1 is my fourth decision variable, then the coefficients of S1 forms the A4 for me. If I assume that S2 is my fifth decision variable, the coefficient of S2 forms the vector of A5. If I assume that S3 is my sixth decision variable, then the coefficient of S3 in the constraints forms the vector of A6. The next notation that we need to learn is the matrix B, which is probably the most important matrix that you need to know to regenerate the final optimal table. B is the m by m matrix, where m is the number of constraints that we have. Since we have 3 constraints, in this example, our B is going to have a size of 3 by 3. So B is a 3 by 3 matrix in this case. Jth element is the column AJ for basic variable J. To form the matrix B, the starting point will be the XBV, this vector right here. The same way that we formed the CBV, remember we found the coefficient of all these decision variables in the objective function. The same way we form B, with the difference that this time for every single decision variable here, we find its associated AJ and we form the matrix B. Let's see how we do this. So XBV is S1, X3, and X1. Now I have to bring the coefficient of every single variable in the constraints to form the matrix B. And we already have the coefficient of S1 in the constraint in this vector here. So the first element of the B will be the coefficient related to S1 in the constraints, which is already given by vector A4. So again, for X3, I have to bring the coefficient of X3 from the constraints. And we know that this is a vector that represents those coefficients. So the second column will be 1, 1.5, and 0.5. And then I have to bring the coefficient of x1 in the constraints. And we know that these coefficients are given here. Now we can form the third column of matrix B. Now we have formed the matrix B. It's easy also to form the matrix NB, which is the matrix of non-basic variable. So it's a n by n minus m matrix, because if I have 6 decision variable and already put 3 of them in matrix B, I'm only left with another 3 to form the matrix of non-basic variables. So in this case, we're going to have a 3 by 3 matrix NB that has all the coefficient of non-basic variables in the constraints of the problem. So again, let's start with XNBV because we have all the non-basic variables in XNBV, and bring all the coefficients of the decision variables here. So the first column of this matrix are the coefficient of x2, and we already know that these are given here. So we bring that vector to form the first column of this matrix. The second decision variable is S2, and this is the column that represents the coefficient of S2 in the set of constraints. And then S3, the coefficient related to S3 is given by a 6 vector, and then we just copy that here and we form matrix NB. Now we learn all the notations for matrix calculation. We are good to start looking at the formulas that we need to regenerate the final optimal table. So this is the maximization problem that we looked at, and we were given that in the optimal table we have S1, X3, and X1 as our basic variables. And we had matrix XBV, XNBV. We found the coefficient of this decision variable in the objective function, and formed matrix CBV and CNBV. Also, we found the coefficients of all the decision variables and the constraints, and we formed vector AJs. Then we formed a matrix B by putting the AJs related to the basic variables, and also we formed the NBV by putting the coefficient of the non-basic variables in the constraints. One thing that you have to pay attention and is that the matrix B and CBV should have the same order. If I'm putting decision variable in the order of S1, X3, and X1, I have to make sure that I stick to the same order for forming the matrix B. As far as we're consistent, we're not going to have major issues, but if we start changing the orders from one vector to the next one, then we're going to calculate wrong values for our final table. So make sure that you go always based on the XBV vector and form all your CBV and B. That way you are consistent and you assure that your final calculations are correct. Now let's look at the formulas to regenerate the final table of a simplex method. So if I have a final table, usually we know that the basic variables will sit in the left hand side, and we have two sets of variable at the end. One set are non-basic variable and one set are basic variable. Usually we see an identity matrix beneath the basic variables and some coefficient under the non-basic variables. Also in the row of Z we see 0 for basic variables and some values for non-basic variables. Now if I'm in the final table of a maximization problem and I have reached the optimal solution, all the non-basic variable here should have a positive value because we have reached the final table. Also, we have objective function and right hand side. These are the formulas I usually see in the final optimal table. You see an identity matrix for basic variable and 0 in the row of Z. And for non-basic variable, we see a B inverse AJ. For Z, you see CB, B inverse AJ minus CJ. For right hand side, you see B inverse B. And for the objective function, you see CBB inverse B. In this lesson, I'm not going to talk about how we get to these equations and how we can drive this equation. Maybe in a separate video, I'll explain about that. But we are most focused on how we can use these formulas to regenerate the final optimal table. But understanding the formula and how these are put together, it's not very complicated, and maybe we'll talk about them in a separate video. But let's see how we can get to use those matrices that we have defined earlier to regenerate the final table of the simplex method. So let's form our table according to what we see in the left hand side. So this part should be the basic variable. We already know that S1, X3, and X1 are basic variables. I keep the same order here as well. And this part, which is related to non-basic variable, I write all the non-basic variables that I already defined in the X and BV. So I just copy them with the same order. Here, only for this part, it doesn't matter what order you choose, but I want to keep everything consistent, so I follow the same order as our X and BV as well as the left hand side formulas. Now I have to put the XBV now, which is this set of decision variables, S1, X3, and X1. Now that we have formed this template, I can calculate all the numbers that should be put in the final table. So it's straightforward. We know already that we have an identity matrix for decision variables that are basic. But for the majority of calculation here, if you notice, we need B inverse. B inverse, B inverse here, and B inverse here as well. So let's calculate B inverse. We already have the matrix B, right? We already have it here. You can calculate the B inverse, and from there you can calculate this part as well as this part. Now that I have calculated B inverse, let's calculate the right hand side, which is the value of decision variables in the final table. But what is vector B? Vector B is the vector of the problem right hand side. So B will be 48, 20, and 8. So this part is B inverse, and this is matrix B, which is the right hand side of your constraints. And the result will be 24, 8, 2. So this is actually the right hand side of your final optimal table in the simplex method. So let's copy that here. Now let's calculate the B inverse AJ for non-basic variables. Because for the basic variable, we already know that we have to have an identity form. We know that for S1 and S1, we have to get 1, and everything else in this column must be 0, including the coefficient in the row of Z. Same applies for X3, so X3 and X3 should be 1, and everything else in this column should be 0, including the row of Z. Also, X1 and X1 should be 1, and everything else in this column should be 0, including the row of Z. But for finding the coefficient of non-basic variables, here I have to use this equation here, which is B inverse AJ. Let's calculate the B inverse AJ for non-basic variables. So for calculating this formula, we only use the AJs related to the non-basic variables that are given on top of this table here. So the first AJ that I have to use is the AJ related to X2, this vector, related to S2 is this vector, and related to S3 is this vector. So these are the vectors that I have to use and multiply them by B inverse to find the coefficients. Here, let's do that and see what value we get. So one way is to calculate the B inverse AJ for every single AJ that we have. One way is to put all these AJs in one matrix, which we already saw, NBV, and do this operation once for all. So that's what I did. So I'm multiplying the B inverse by NBV, which is this vector, because we already know that this is formed by putting the column related to non-basic variables coefficient in the constraint. So this is the same thing as we put all these AJs together and calculated all the coefficients at one shot. So let's copy these coefficients in the final table. Again, it's important to notice that since we were consistent in terms of putting the decision variables in our vectors, the first one represents X2, and then you have S2 and S3. If you had different orders, or if you had put your decision variables in a different order here, you have to really be cautious about copying these values under decision variables. But since I kept the order consistent, I just easily copy these coefficients here and for my table. Now the only thing that we are left with is this part, as well as the objective function here. For forming the objective function, it's easy to plug in the value of decision variables into the objective function and find the value of objective function, but let's practice the use of formulas that we have here. Alright, this is what we have gotten so far. We also have the value of 0 for the basic variables in the row of Z. Now let's calculate the value of row of Z for non-basic variables here using this formula. So CB B inverse AJ minus CJs. Remember, again, since we're solving this only for non-basic variables, the AJ and CJ here is only related to non-basic variables. So only for non-basic variable we do this calculation. Why? Because if you do this calculation, CB B inverse AJ minus CJ, for basic variables you always get 0. So we don't bother to do the calculation. We already know that for basic variables we get 0. So let's just calculate these coefficients for non-basic variables that we have. Alright, so the first part of this formula is CB. We already formed the CB or CBV, which is the coefficient of basic variables in the objective function. So we had the XBV, which is the set of decision variables, and we found their coefficients in the objective function earlier. So this is the vector related to CB. And then the next part of this formula is B inverse AJ. And we have to do this for all the non-basic variables. But we already calculated the B inverse AJ up here. So instead of writing B inverse AJ again, I just copy this matrix here because that's already the calculation of B inverse AJ. So for that part of the formula, I just put the B inverse AJ and I don't recalculate the numbers. So far we have CB and we have B inverse AJ. Now we have to put the CJ. CJ is the coefficient of non-basic variable. But since I put all the non-basic variables and I'm solving everything in one try, I have to put a vector of XNBV and their coefficient in the objective function that we already calculated. So Cj, it's the coefficient related to x2 in the objective function, which is 30. And since we don't have s2 and s3 in our objective function, their coefficient is 0. And if I look at these elements, each of them is a Cj. So everything here is also an AJ. So you could have calculated this for just one decision variable by putting the CB, B inverse AJ for one decision variable, let's say the first one, minus the CJ related to that decision variable. So this only gives you the coefficient related to the first non-basic variable, which is x2. But instead of calculating it separately, I put everything in one vector and calculate everything in one try. So the value, the final value, and that we usually show by C bar, are the coefficient of non-basic variables in the row of Z. So let's copy those. We have 5, 10, 10 in our table. Now the last thing to calculate is the objective function. We know that the formula for objective function is CB B inverse B, and we already calculated the B inverse B. It's our right hand side, so I just need to multiply the CB by the right hand side that we just found and calculate the objective function value. Another alternative way would be just plug in the value of the decision variables in the objective function, because we have found the value of decision variables here. We know that x3 is equal to 8, and also x1 is equal to 2, and the value of x2 is 0 because we don't see the x2 here. x2 is out of the basis, so it's a non-basic variable, and its related value is 0. So if I plug in to the objective function, I get the value of 280. But let's try the calculation of objective function using the CB inverse B. As I mentioned earlier, the B inverse B is our right hand side. Remember, we used the B inverse B to calculate this part, so I don't need to recalculate that section. So I just copy the B inverse B here and multiply it by CB. Remember, CB was the coefficient of basic variables in the objective function. So if I multiply these two, I get 280, and as you see, both give you the same value for objective function. So these are alternative method for calculation of objective function. Now you can copy the value of objective function in the table, and your final simplex table is complete. You have found the final table without actually going through all the intermediate steps of the simplex table. The only information that you need at the beginning to start the problem and solve all these values is the set of decision variables that are basic at the end. Now, why this is important? You might raise the question that if I know what are the basic variables in the final table of simplex, what's the point of resolving this? Because apparently I have solved the problem and I have gotten to the point that I know what the basic variables are. But the answer to this question is the subject of this lesson, which is sensitivity analysis. Let's say if you have found this final table, and you're faced with questions such as, what if we increase the amount of available resource for the first constraint? How that would change the final table? What if we increase the cost related to the second decision variable? Is it going to change the final table? What if we increase the amount of resource for the third constraint? What if the profit for the third decision variable has dropped? For answering these type of questions, you don't want to recalculate the whole simplex table from the beginning. If you know how to recalculate these numbers given the final basic variables, you can regenerate the final table with those changes and see how they will change your final table. That's the benefit of knowing the matrix math for simplex. We're going to talk about all these changes in the next lesson. Now that we have learned how to regenerate the final table of simplex given some basic variables, we are good to start the sensitivity analysis lesson and see how some changes in an initial problem can change the final table. We are done with the first part of the sensitivity analysis lesson. Please refer to your blackboard for your assignment. Thank you.